Let's begin. So at the previous lecture, we recalled some basic stuff from a standard course of functional analysis. Namely, we recalled some basic notions of elementary spectral theory in Banach algebras. One final portion of this theory, which we had no time to discuss at the previous lecture, is the spectral radius formula. So let's recall it now. Suppose that A is a unital Banach algebra. And suppose that little a is an element of our algebra. By definition, the spectral radius of A is a number defined as the following supremum. Here lambda runs over the spectrum of A. This is well defined because we know that the spectrum is non-empty. Oh, of course, we assume from the very beginning that the algebra is non-zero. So the spectrum is non-empty and the spectral radius is well defined. Let's recall that we have Glyphon's theorem, which states in particular that for each lambda in the spectrum, the absolute value of lambda is less than or equal to the norm of the element. So Glyphon's theorem implies that the spectral radius is less than or equal to the norm of A. In some important cases, this is actually an equality. Here's the simplest example. Suppose that A is the algebra of bounded functions on some set X, equipped with the supremum norm. So in this case, we know that the spectrum of A, of little a, of each element of this algebra is the closure of range of this function. So it's this implies that the spectral radius equals the supremum norm. And the same equality holds for some other function algebras. For example, the same holds for the algebra of continuous bounded functions on a topological space. Another example of the same kind. Suppose that A is the algebra of bounded linear operators on a finite dimensional Hilbert space. So H is a finite dimensional Hilbert space. And suppose that little a is an operator, an element of our algebra, such that A is given by a diagonal matrix with respect to some orthonormal basis of H. In this case, the spectrum of this operator is, of course, the set of numbers which are on the diagonal. And so the spectral radius is the maximum of the absolute values of these lambda i's. And since this is a diagonal operator, it's easily seen that the norm is also equal to this maximum. So again, in this case, the spectral radius equals the norm. Now let's look at an example of a different situation. Suppose that A now is the algebra of bounded operators on the two-dimensional space. So this is essentially the algebra of 2x2 matrices. And let little a be the following matrix. Well, the spectrum of each upper triangular matrix again consists of those numbers which are on the diagonal. And since we have zeros on the diagonal, we conclude that the spectral radius is 0. But of course, the norm of A is not 0 because the element is not 0. So in this case, the spectral radius is strictly smaller than the norm. This example actually can be generalized as follows. We have the following useful exercise. If our algebra is more or less arbitrary, little a is an nilpotent element, then the spectrum of A is 0, and hence the spectral radius is also 0. But of course, there are many algebras which contain non-zero nilpotent elements. So for such elements, the spectral radius is again strictly smaller than the norm. In a general case, we have the following useful formula for the spectral radius. This is the so-called Birlingel theorem. If, again, A is a unital Banach algebra, and little a is an element of our algebra, then the spectral radius of A equals the following limit. And the same number is equal to the infimum of elements of the sequence. Well, actually, this theorem is due to Glyphon in full generality. And Birlingel proved it earlier, but only for a very specific Banach algebra, the so-called Birlingel algebra, which is the weighted L1 algebra on the integers. The general case is due to Glyphon. This is a standard result in functional analysis, so I'll not give you the proof. Briefly, the idea of the proof. First of all, this inequality is more or less trivial. It easily follows from the spectral mapping formula. And the opposite inequality is not so trivial. So the idea is to take an arbitrary bounded linear functional on A and consider the following function, which takes lambda to the following complex number. This function is holomorphic in the neighborhood of 0, and its Taylor coefficients can be calculated explicitly. They are equal to the following numbers. So these are the Taylor coefficients at 0. And then by applying the uniform boundedness principle, that is the Banach-Steinhaus theorem, in a suitable way, we get the required inequality. So this is the idea of the proof. As a corollary, we get a characterization of elements whose spectral radius is 0. The spectral radius is 0, if and only if this limit is 0. And explicitly this means that for each positive epsilon, we have the following asymptotics of the norms of powers of A. So they go to 0 very quickly, faster than any epsilon to the power n. So a typical situation is the situation where the norm of A to the power n behaves like something divided by n factorial. So in this case, the element is the spectral radius is 0. And actually, there is a special name for such elements. They are called quasi-nilpotent elements. Such elements are called quasi-nilpotent elements. Obviously, each nilpotent element is quasi-nilpotent because a to the power n is eventually 0. But there are some natural examples of quasi-nilpotent elements which are not nilpotent. Let me give you only one classical example of such an element. An example and exercise at the same time. Consider the so-called Volterra integral operator. This operator will be denoted by Vk. It acts on the big O2 space on a closed interval. And it acts by the following formula. So I claim, so here k is a function of two variables. And I claim this exercise that this operator is quasi-nilpotent for each bounded measurable function k. On the square. This is actually a straightforward calculation. If you try to calculate the norms of the powers of this operator explicitly, then can be estimated as something divided by n factorial. And so this element is quasi-nilpotent. A more difficult exercise is to show that this operator is quasi-nilpotent for each square integrable function k. But this is not so easy. Another useful corollary of the spectral radius formula is as follows. Suppose that A, again, is a unital Banach algebra. And suppose that B is a closed subalgebra of A, such that the identity of A belongs to B. So they have a common identity. In this case, if we take an element little b in the smaller algebra, we know that in general, the spectrum of this element calculated with respect to B is different from the spectrum calculated with respect to A. More exactly, the spectrum calculated with respect to B can be bigger than the spectrum calculated with respect to A. But the spectral radius is the same. I have this equality for the simple reason that they are given by the same formula, which depends only on the norm, only on the norm of A. So it doesn't depend on the choice of the subalgebra B. Okay, so that's all I wanted to tell you about the spectral radius. Our next goal, before we introduce C-star algebras, will be to discuss some basic facts from Glyphon's theory of commutative Banach algebras. And the basic notions of this theory are the maximal spectrum and the Glyphon transform. The maximal spectrum and the Glyphon transform. Sometimes this theory is included in courses of functional analysis, sometimes not. So anyway, I'll give you full proofs of basic results in this field. We start with a purely algebraic situation. Suppose that A is a commutative unital algebra. Both assumptions are essential. Today we assume that A is unital, and it turns out that the non-unital case is also quite important. So we will discuss the new non-unital case at the next lecture. So today A will be commutative and unital. Let's recall the following algebraic definition. Suppose that we have an ideal, a proper ideal of A. We say that I, this ideal I, is maximal. If it is not contained in any strictly bigger proper ideal. There is no ideal J such that J is strictly bigger than I. Well, in other words, a maximal ideal is a maximal element in the set of all proper ideals of A. Of course, I doesn't have to be the biggest ideal. In general, there can be many maximal ideals in the same algebra, which are incomparable with each other. Another equivalent characterization, which is quite useful, characterization of maximal ideals, is given in the following useful exercise. The proper ideal I is maximal if and only if the quotient A modulo I is a field. Okay, we now introduce the maximal spectrum. By definition, the maximal spectrum of A, maximal spectrum of A is the set of all maximal ideals. It will be denoted like this. Here's a useful example and an exercise at the same time. Let's take the polynomial algebra in one variable. So what can I say about its maximal spectrum? Well, the maximal spectrum of this algebra is, there is a one-to-one correspondence between the maximal spectrum and the complex plane. More exactly, if P is a point in on the complex plane, then we can consider maximal ideal MP, which consists of those polynomials that vanish at P. F of P is 0. So the exercise is to show that this is a one-to-one correspondence between the complex plane and the maximal spectrum of the polynomial algebra. In fact, this result extends to the polynomial algebra in several variables, but this is much harder, and actually this is a weak form of Hilbert's Nullstellensatz. Okay, how about the existence of maximal ideals? Well, maximal ideals always exist, and moreover we have the following general result on proposition. Each proper ideal of A is contained in a maximal ideal. In particular, if we start with the zero ideal, we see that maximal ideals exist. The proof is a standard application of Zorn's lemma. So we start with an arbitrary proper ideal, I of A, and we denote by M the collection of all ideals, J. J is a proper ideal of A, which contains I. So this is a pose set, a partially ordered set. The order relation is just the inclusion. It is non-empty because it contains I itself. I claim that the set M satisfies the condition of Zorn's lemma. Well, why is it so? We have to show that each chain in M has an upper bound. Well, indeed. Suppose that C is a chain, which means that each two ideals in C are comparable. One of them is bigger than another one. We have to show that C has an upper bound in M. Well, let K denote the union of all ideals in C. So clearly, since C is a chain, we see that K is also an ideal. And it contains I, of course. We have to show that K is a proper ideal. And here it will be essential that our algebra A is unital. Well, indeed, for each J in C, each J is a proper ideal. So the identity of the algebra is not in J. And since this holds for each J in C, we can conclude that the identity of the algebra is not in K. And so K is a proper ideal. So K is a proper ideal, and it's immediate that K is an upper bound for C. So we see that M indeed satisfies the conditions of Zorn's lemma, and so it has a maximal element. And this maximal element is clearly a maximal ideal, which contains I. So this completes the proof. By the way, in the non-unital case, for non-unital algebras, this result fails. One can construct some examples of ideals in non-unital algebras which are not contained in any maximal ideal. This can be corrected somehow, but I postpone this for the next lecture. Okay, let's now introduce another set which is closely related to the maximal spectrum. We define the character space. Character space of A to be the set of all non-zero characters. And we denote it by A hat. So let's recall that a character is a homomorphism to the base field, to the field of complex numbers. A set of all non-zero characters. And let's also recall that in this situation, non-zero is equivalent to unital. So each non-zero character of a unital algebra takes the identity to the identity. Let's now observe that there is a simple relation between the character space and the maximal spectrum. Namely, for each character chi of A, for each non-zero character, its kernel is clearly a maximal ideal of A. It is maximal for the obvious reason that it has codimension 1. It's a kernel of a bounded. It's a kernel of a linear function, so it is a vector subspace of codimension 1. So it is obviously maximal. So we have a map from a hat to the maximal spectrum, from the character space to the maximal spectrum. I claim that this map is always injective. The map from the character space to the maximal spectrum, which takes each character to its kernel, is injective. Well, this is very easy, actually. Here we have two characters, say chi1 and chi2, such that they have the same kernel. Then they are the same up to multiplicative constant. This is true for any two linear functionals. And if we now evaluate them at the identity, we see that chi1 of 1 is 1, but on the other hand, chi2 of 1 is also 1, and so this implies that lambda is equal to 1. So the characters are the same. And so our map is injective. In some special situations, this map is also bijective. Here's a simple example and exercise at the same time. For example, if A is, again, the polynomial algebra in one variable, then this map is a bijection. And in fact, this result holds for each finitely generated algebra over the complex numbers. On the other hand, if we take any field which properly contains the complex numbers, but then it's easy to show that the character space is empty. There are no characters no non-zero characters to the complex numbers. But on the other hand, clearly the maximal spectrum is not empty because the zero ideal is maximal. So the maximal spectrum consists of the zero ideal. So in this case, our map is not a bijection. It turns out that this map from a hat to the maximal spectrum is a bijection provided that A is a Banach algebra. And to prove this result, we need the following lemma. Suppose that A is a commutative unital Banach algebra. then each maximal ideal of A is closed. Well, indeed. Let's take maximal ideal I. And observe that the continuity of the algebraic operations in our algebra implies that the closure of I is also an ideal. Okay, now suppose that I is not closed. Suppose that I is not closed. So the closure is strictly bigger than I. And since I was maximal, this can happen in the only case where the closure of I is not a proper ideal. It is equal to A, which means that I is dense in A. But we already know that the set of all invertibles in A is an open set. So since I is dense, we conclude that the intersection of I with the set of all invertibles is non-empty, because this set is open. Because A cross is open in A. But if an ideal contains an invertible element, it coincides with the algebra. I equals A, and this is a contradiction. So this completes the proof. So we conclude that I is closed. As a corollary, we see that a commutative unital Banach algebra doesn't have dense proper ideals. Because each proper ideal is contained in the maximal ideal, and the maximal ideal is always closed. So a proper ideal cannot be dense in A. Okay, now we can prove the following result. Theorem: if A is a commutative unital Banach algebra, then the map from the character space to the maximal spectrum, which takes each character to its kernel, is a bijection. Before we prove this result, let's make a simple observation. If A is a Banach algebra, not necessarily commutative, an arbitrary Banach algebra, and if I is a closed two-sided ideal, then the quotient of A modulo I is also a Banach algebra. With respect to the canonical quotient norm. The quotient norm is given by the following formula. Well, we know from the standard functional analysis course that the quotient of a Banach space modular closed vector subspace is Banach space. We also know that the quotient of any algebra by a two-sided ideal is an algebra in the initial way, and so we need only check that this quotient norm is submultiplicative. But this is very easy. Okay, now we are ready to prove this theorem. We already know that our map is injective. So now we have to show that each maximal ideal is a kernel of a character. So let I be a maximal ideal of A. We take a quotient. And we observe that this is a Banach field. It's a Banach algebra because I is a closed ideal, and it's a field because I is maximal. Now, the Glyphon-Transform theorem implies that this field is a field of complex numbers. Now we look at the following picture. So this is A. So we have quotient map of A onto the quotient of A modulo I. And we have an isomorphism between this quotient and the complex numbers. And of course, the composition of these two maps is a character, is homomorphism from A to the complex numbers. And clearly I is the kernel of this character. So this completes the proof. As a corollary, we get the following useful invertibility criterion for an element in a Banach algebra. Again, if A is a commutative unital Banach algebra, and little a is an element in our algebra, then this element is invertible, if and only if for each character, for each non-zero character of A, character chi of A is not equal to 0. Well, indeed, the left-to-right implication is clear, because chi is a unital homomorphism, and the unital homomorphism takes invertibles to invertibles. And to prove the right-to-left implication, suppose that A is not invertible. If A is not invertible, then we consider the principal ideal generated by A, and this will be a proper ideal. So the principal ideal generated by this element is proper. So it is contained in the maximal ideal. But we already know that I is the kernel of a character. So a little a is contained in the kernel of a character, which means that chi of a is 0. And this completes the proof. Okay, so from now on, we adopt the following standard and convenient convention. We'll always identify the character space with the maximal spectrum. By means of the standard bijection. This is quite convenient because in some situations it is more convenient to look at the elements of the set as at characters, and in other situations it is more convenient to interpret them as maximal ideals. So we will always identify these two sets. Okay, so so far the maximal spectrum of A is just a set. And our next goal will be to introduce a topology on this set to make it into a compact topological space. Before we can do it, let's make a short digression and let's recall some basic facts on the weak star topology. So suppose that E is an Nernst space. And for each element, say little v in the space, we define a semi-norm. Define a semi-norm denoted like this. This is semi-norm on the dual space with star by the following simple formula. This is just the absolute value of f of v. And by definition, the weak star topology on the dual is the locally convex topology generated by all semi-norms of this form, generated by the family of all such semi-norms. Oh, okay, so this is the formal definition. Just in case, if some of you forgot what the topology generated by a family of semi-norms is, let me state this more explicitly. So if f is an arbitrary bounded linear functional on E, the standard subbase of neighborhoods of f for the weak star topology, of course, is the following family, as denoted by sigma f. It consists of all kind of balls, u, v, epsilon of f, where v runs over E, and epsilon is a positive number, and the respective ball, u, v, epsilon of f, consists of those functions g on E, such that the following inequality holds: g of v minus f of v is less than epsilon. So once we know the standard subbase of neighborhoods of each element, we can easily recover the topology. So if we consider all such balls for all f, we get a subbase for the weak star topology, and if we add finite intersections, we get a base for this topology. Okay, let's now recall some basic facts on the weak star topology. First of all, this is fact 0. The weak star topology is always Hausdorff. This follows from the Hahn-Banach theorem. Next, if we equip X star, it was E star, yeah? E star with the weak star topology. So of course, this space of bounded linear functionals is contained in the space of all complex valued functions on E, C to the power E. And I claim that the weak star topology is nothing but the restriction to the dual space, to E star, of the standard product topology. Or the Tikhonov topology. On C to the power E, on the space of all complex valued functions on E. The next few facts are just corollaries of this observation. Namely, if we have a sequence in E star, then it converges with respect to the weak star topology, even only if it converges pointwise. Also, the weak star topology. Well, before stating this, let's introduce some notation. So for each element V in E, let epsilon V denote the respective evaluation functional on E star. Epsilon V of F equals F of V. So I claim that the weak star topology is the weakest topology on E, that makes all such functionals continuous. This is more or less also immediate from the fact that this is the restriction of the Tikhonov topology. Property 4, which is also quite convenient. Suppose we have an arbitrary topological space, X, and a map phi from X to E star, where E star is equipped with the weak star topology. I claim that it is continuous, if and only if for each vector in E, phi composed with the evaluation functional, so this is complex valued function, is continuous. Again, this is essentially the characteristic property of the product topology. Property 5. Well, let's consider the canonical embedding of I into the bidual, of E into the bidual, the canonical embedding I of E into E double star. So this map takes V to epsilon V. And I claim that the image of this canonical embedding consists precisely of those functionals in the bidual which are weak star continuous. This is also a standard fact on the weak star topology. Fact number 6. Suppose I have two normed spaces, E and F. And suppose that we have a linear map, linear operator T from F star to E star, where the duals are equipped with the weak star topologies. Then T is continuous, if and only if it has a predual. So if and only if there exists a linear operator, a bounded linear operator S from E to F, such that S star equals T. We will need only only the right to left implication. That is, the dual of each bounded linear operator is weak star continuous. And probably the last fact about the weak star topology, which we need, is the Banach-Hollow theorem. This theorem states that if we take the closed unit ball of the dual space, then this ball is a weak star compact. Of course, it is not compact for the norm topology, unless E is finite dimensional. But it is always weak star compact. This is the Banach-Hollow theorem. Okay, so this was a short digression about weak star topology. Now let's come back to commutative Banach algebras. So we can now topologize the maximal spectrum. So suppose that A is a commutative unital Banach algebra. By definition, the Glyphon topology on the maximal spectrum array, which is canonically identified with the character space, is the restriction to a hat or the weak star topology on A star. By the way, let's recall that all characters are continuous automatically. So A hat is a subset in A star. So the maximal spectrum becomes a topological space. Well, what can we say about this space? We have the following theorem. Maximal spectrum is compact and Hausdorff. Well, first of all, we already know that the weak star topology is Hausdorff. A star is Hausdorff for the weak star topology. And hence, so is A hat. Now, why is it compact? Well, we also know that A hat is contained in the unit ball of A star. The norm of each character is less than or equal to 1. And we also know that the unit ball is a weak star compact. So to show that A hat is compact, we have to show that it is closed in the unit ball. because a closed subset of a compact space is compact. Well, why is it closed? We take any two elements in A, say little a and little b, and we observe that the following two maps are continuous. So the first map takes each f to the following number, f of ab minus f of a, f of b. And the second map is just the evaluation at the identity. So they are continuous with respect to the weak star topology. Well, indeed, the second one is just the evaluation map, and the first one is reduced to evaluation maps. So it's we have the product of two evaluation maps, which is continuous, and the difference of two continuous functions is obviously continuous. So both of them are continuous. And now the character space A hat consists of those functionals, of those elements in A star, such that f of a b minus f of a, f of b is 0. So this means that f is a character, and such that f for each a and b, this means that f is a character, and second, such that f of 1 equals 1. This means that f is unital or equivalently non-zero. So now this observation, together with the continuity of the above two functions, readily implies that A hat is closed. A hat is closed in the unit ball, and this implies that it is compact. Okay, so the maximal spectrum becomes a compact Hausdorff topological space. Now we are ready to introduce the Glyphon transform. So we give the following definition. The Glyphon transform of an element little a in our algebra is a function A hat on the maximal spectrum. This is a complex valued function given by the following simple formula. So here we interpret little x as a character and just evaluate this character at A. I claim that the Glyphon transform of each element from our algebra is continuous. Position A hat is continuous. The proof is very easy. Well, indeed, if we look at the definition of A hat, we see that A hat is nothing but the following element. We take the canonical image of A in the bidual and restrict it to the character space. And we have already recalled that the canonical for each normed space, the image of the space under the canonical embedding in the bidual consists precisely of those functions which are weak star continuous. So this element is weak star continuous on A star. And that's it. This completes the proof because, of course, the restriction of any continuous function is continuous. So for each element in our algebra, we have constructed a continuous function on its maximal spectrum. So we have a map from A to the algebra of continuous functions on the maximal spectrum. And this map is called the Glyphon Transform of the algebra. So by definition, the Glyphon Transform of the algebra A is a map gamma A from A to the algebra of continuous functions on the maximal spectrum, which takes each element little a to the function a hat. We have the following theorem, which tells us something about the basic properties of the Glyphon transform. So again, we suppose that A is as above. A is a commutative unital Banach algebra. Again, once again, I stress that it is essential that it is unital. For non-unital algebras, we will also be able to define the Glyphon transform, but it's not exactly the same. So its properties are a bit different. First of all, I claim that the Glyphon transform is a unital algebra homomorphism. Unital algebra homomorphism. Second, the norm of gamma equals 1. Of course, if the algebra is non-zero. Next, for each element on little a and a, the norm of its Glyphon transform, I mean the uniform norm, is equal to the spectral radius of A. Property 4, for each element in our algebra, little a, the spectrum of A is equal to the range of its Glyphon transform. That is the image of the maximal spectrum under the function a hat. And finally, the kernel of the Glyphon transform is the intersection of all maximal ideals. And the same set is equal to the set of all quasi-nilpotents in our algebra. Okay, so these are the basic properties of the Glyphon transform. It will be convenient first to prove, well, first of all, property 1 is more or less clear. It's a simple algebraic exercise, which is immediate from the definition, to show that gamma is a unital homomorphism. Now let's look at part 4. So the right-hand side of this equality, I mean the range of little a hat. So the little a hat is a continuous function of the maximal spectrum. So its range is equal to its spectrum. So we know that the range of a hat is the spectrum of a hat in the algebra of continuous functions. So basically, we want to show that gamma is spectrum preserving. Our homomorphism gamma preserves the spectrum. And we have already discussed in the previous lecture that a unital homomorphism preserves the spectrum, even only if it takes non-invertibles to non-invertibles. So this equality implies that it suffices to show that gamma takes non-invertibles to non-invertibles. Okay, so suppose that little a is a non-invertible element in our algebra. And let's recall the invertibility criterion, which was proved at the beginning of our lecture. So this means that there is a character, a non-zero character, which vanishes at a. There is a character chi, such that chi of a is 0. That is, this means that the Glyphon transform of a vanishes at chi. So a hat is a non-invertible element in the algebra of continuous functions. This is equivalent to say that gamma preserves the spectrum. So this completes the proof of part 4. Well, now we observe that part 3 is immediate from part 4 because, the spectral radius is less than or equal to the norm. This was a remark about part 2. So if we want to prove part 3, we just take the supremum in part 4, and we get that the spectral radius, this is the supremum of the absolute values of points in the spectrum, is equal to the supremum of this of the elements in the range. That is to the supremum norm of a hat. So 3 is immediate from 4. Now, part 2. Part 2 is almost immediate from part 3 because we know that for each element in our algebra, the spectral radius, which is the same as the norm of the Glyphon transform, is less than or equal to the norm of A. And this means that the norm of the Glyphon transform is less than or equal to 1. But on the other hand, gamma is unital. It takes the identity to the identity. And so its norm is exactly 1. Okay, and finally, we have to prove part 5 about the kernel of the Glyphon transform. Well, if we look at the definition of the Glyphon transform, we see that this is the intersection of the kernels of all characters. Also, because of the bijection between the character space and the maximal spectrum, this is the intersection of all maximal ideals. On the other hand, if we apply part 3, we see that the kernel of the Glyphon Transform consists of those elements for which the spectral radius is 0. That is, it consists of all quasi-nilpotent elements. And this completes the proof. Okay. By the way, the intersection of all maximal ideals is quite a canonical ideal, which makes sense for each unital algebra, not necessarily a Banach algebra. It is the so-called Jacobson radical. If A is a unital commutative algebra, then the Jacobson radical of A is noted by J of A is the intersection of all maximal ideals. And we say that A is Jacobson semi-simple if its Jacobson radical is 0. So what we have just proved is that the Jacobson radical of a commutative unital Banach algebra is nothing but the kernel of the Glyphon transform, and it consists of all its quasi-nilpotent elements. By the way, it's interesting to compare this with another classical object from commutative algebra, namely the nil radical, which consists of all nilpotents, and which is in general strictly smaller than the Jacobson radical. There are many examples of algebras which are Jacobson, for which the Jacobson radical is strictly bigger than the nil radical. In particular, we can even construct an algebra without 0 divisors. So the nil radical is trivial, but the Jacobson radical is very big. This will be a good exercise in one of our optional exercise sheets. Okay, in conclusion, let me formulate a very simple but useful corollary of our theorem. The image of the Glyphon transform is spectrally invariant. Spectrally invariant in the algebra of continuous functions on the maximal spectrum. Which means that you have an element in this subalgebra, in this image, which is invertible in the algebra of continuous functions, then it is invertible in this subalgebra. Well, indeed, if we have an element which is in the image and which is invertible in the algebra of continuous functions, then since gamma preserves the spectrum, we already know that gamma preserves the spectrum, we conclude that A should be invertible in the algebra A. But this obviously implies that the inverse element sits in gamma, in the image of gamma. So our initial element is invertible in the image of gamma. And that's it. So everything follows from the fact that gamma preserves the spectrum. Okay, so that's all for today. And at the next lecture, we consider some concrete examples of the Glyphon Transform. In particular, we discuss the Glyphon Transform for some subalgebras in the algebra of continuous functions on the compact Hausdorff space. We briefly discuss some functorial properties of the Glyphon Transform. Then we discuss the non-unital case briefly. This is also quite important. So in contrast to pure algebra, in C-star algebra theory and more generally in functional analysis, non-unital algebras are quite important. And then we will be ready to introduce C-star algebras and to study their basic properties. Okay, thank you.